So welcome to the second session of the Robust Vision Challenge 2020. My name is Oliver Zendel, and we already had a first session, and there is an introduction video with our motivation and the background. So we'll be very brief. The idea of the Robust Vision workshop is to combine multiple benchmarks into one meta ranking. We do that for multiple computer vision tasks so that we can evaluate more robustly the real performance on the task level, not on the data set. So this is one of our approaches to reduce dataset bias and gamification that is happening currently on leaderboards. This is a joint effort of a lot of people. So we have 28 organizers. It was a lot of work, so thanks again. You can see all of them here and have a look at the team page. It was a lot of work, and thankfully I had a lot of hands to help me with it. Of course, we also have to thank all the sponsors again. Thank you to the golden sponsors, Apple, AIT, Google, and Intel, and to the silver sponsors, Naval Labs Europe and Mapillary Research, for sponsoring the workshop and making this possible. Also, a reminder, we have 3 keynotes. One from Ross Gershik about robustness across the data abundance spectrum. One from Kwok Lee about noisy student training on robust vision, and one from Alexander Matri, what do our models learn? And they can all be found on the ECCV virtual conference platform and in a few hours or in a few days on the Robust Vision Net website. Okay, so without further ado, the competition winners were announced in the first session. This is just an overview slide. You can see them here. And we want to maximize the time that participants have to give their talks. So I would suggest we already start with the very first talk. Raft, TF, if you're ready to present, please share your screen now.
I cannot share my screen. Can you exit first? Okay.
Sorry, yes, it should work now.
Okay, can you see my screen now?
Yes.
Okay, great. It's a great pleasure to talk about our entry to the optical flow track, a TensorFlow implementation of Raft. It's joint work with my colleagues at Google. So first, let's briefly review the Raft, which stands for Recurrent All Pairs Field Transforms. And the paper just received the ECCV 2020 Best Paper Award. So given an input image pair, Raft will first extract features which they use to construct a full cost volume. The features, the cost volume are at the 1/8 resolution. And they further construct a cost volume pyramid to deal with large motion. And Raft also extracts a context feature, which is used for the gated recurrent refinement unit. So at each recurrent refinement step, it will look up from the full cost volume around the current flow estimate, look up the cost volume and feed it to the refinement unit to get the refinement of the flow field and add to the initialization. And this step can be repeated many times during inference. And after you get the flow field at the 1/8 resolution, so Raft further introduces an upsampling module, which is very similar to the subpixel convolution for image super resolution. And it actually achieves a significant improvement over the previous state of the art, like about 60% improvement on KT and about 30% on Syntax. This is a very remarkable achievement, especially given that previous methods tend to get saturated on these benchmarks. And some other features is, so Raft is actually quite fast to train, faster than previous methods. And after it is trained on flying chairs and flying things, it can generalize much better on the real KT dataset. And so compared with the official PyTorch implementation, we made some changes in our TensorFlow implementation. So first, for the architecture, we did not use batch norm or dropout in the network structure. And for the optimization, we do not apply weight decay for the Adam W optimizer. And with all these changes, we have to basically search against the initial learning rate by looking at the performance on a validation set. And one of the major difference is, so our data augmentation is based on the data augmentation scheme by FlowNet or PWCNet or VCN with some small modifications. But first, let's see the difference between the major differences in data augmentation between the PyTorch Raft and that by FlowNet or PWCNet. So for spatial augmentation, so the PyTorch version of Raft doesn't have the rotation, but it adds an additional vertical flipping with a probability of 0.1. And by comparison, the FlowNet type of augmentation will additionally apply a small augmentation to the second image to make the dataset more diverse. And for the color augmentation, so the major component of PyTorch Raft is using the color jitter function by in PyTorch. And it also introduces occlusion by erasing rectangle regions in the second image. And further, it applies an asymmetric color augmentation. That is, apply separate color augmentation to the two input images with a probability of 0.2. And by comparison, the FlowNet kind of augmentation will project the image color into a PCA space and perturb the PCA coefficients before projecting back. And there is an additional small augmentation applied to the second image. And our augmentation scheme is basically based on this one, but we make following changes for different stages. So for the first pre-training on flying chairs, we add the vertical flipping from Raft and also the random channel swapping from DD-Flow or self-flow. And when we fine-tuning on flying things 3D, we reduce the amount of spatial augmentation by decreasing the range for rotation. And PyTorch Raft also reduces the range of spatial augmentation by decreasing the range of scaling. And finally, when we do the last stage fine-tuning, where we use multiple data sets, we use 5 data sets with the following probability to sample from them. So basically, we sample Sintel and KT plus Viper using roughly the same probability. And then we use the additional flying things 3D and HD1K, gives them a relatively smaller probability. And the ratio is taken from the VCN paper. And some additional thing is we have to downsample the Viper and HD1K data because their resolution is much higher, around 2000 pixels in width. And we also need to reduce the probability of performing spatial augmentation for the driving scenario, because the spatial changes for the driving scenes tend to be smaller than the more generic thin-tail or flying things. And further, we do not add the Gaussian noise during this stage. And so this is what we train the raft in TensorFlow. And it works kind of pretty well on the optical flow track. It's ranked first in 3 out of the 4 benchmarks. And now let's see some individual benchmark. So on thin-tail, our implementation of raft is only behind the official PyTorch raft, which uses multiple frame information. And if we compare with their two-flow version, the performance are very close. Also on KT, our implementation that's trained using the 4 datasets is kind of also close to the official raft in PyTorch, which has been especially fine-tuned to KT dataset. It is ranked first on the Viper dataset. And if we look at some of the examples, we can see it can recover very fine details in the Viper test images. And on the Midberry, it's kind of surprising, at least to me, it performs very well because it did not see the Midberry training data, and we also did not use the Midberry data as a validation set. And as you can see on these images, the flow errors tend to be very small, and some small amount of error happened around the motion boundaries or occlusion boundaries. Some questions is where is the method not robust? And if we look at some of the examples from the test set, we can see, for example, on KT, when there is strong lighting effects, our implementation has big error in the flow field. And also in the textureless sky region, in the Viper dataset, you can see it also caused a big error, like this red region. And also for the front of the car, it also seemed to cause some artifacts. And another place where it is not robust is the input image resolution needs to match the training image resolution, which is thin-tail or KT. So if we just run it on the original resolution on Midberry, on this sequence on Midberry is kind of small, you can see there are strong artifacts compared with the ground truth. The details cannot be recovered very well. So our remedy is we can upsample the images to around thin-tail resolution, apply our method, and then downsample the flow field, which can recover these motion details quite well. But I think the future work should be developed to make such network be more robust to the image resolution. And that's all for my talk, and thank you for your attention.
Okay, thank you for your talk. I see we already have a question in the Q&A. Why are you using the FlowNet data augmentation instead of the regular PyTorch raft? Or just combine both to get more augmentations?
So this is actually, we found it, as you can see, we took some augmentation from raft, and from our empirical results, we found this one turned out to work much better for our TensorFlow implementation.
So did you start with the original raft papers augmentations and then modified them basically, or?
So we tried to re-implement the original raft augmentation, but in TensorFlow it did not work as well as say this kind of augmentation. Yeah, that's the reason we switched to line or augmentation, and it took some steps from the raft augmentation.
I see. Thank you.
I have a few questions.
Daniel, please.
So first, a technical detail. Does the original Raft paper produce a flow at 1/8 of the resolution? Is that correct? And if so, is that also what you do, or do you what is the output resolution compared to the input resolution?
You mean for which one?
For the original Raft, and then for your version of Raft.
So I think in principle, both network can output arbitrary resolution. So for any input resolution, it should output the same resolution. But for our implementation, we found that the issue is if the input resolution doesn't match the training resolution, the performance is not the best.
I guess what I'm asking is, if you just download the PyTorch Raft code, doesn't it output the flow field at like 1/8 of the resolution? But what
no,
you're saying is
it outputs the full resolution.
Oh, so you don't need to do any sort of upsampling from the output using guided filters or something?
No. So Raft introduces a module called an upsampling module. That is included in their camera ready, but not in the first version of their archive paper. So for that one, the idea is kind of similar to the subpixel convolution in image super resolution. So basically, for every shift at the 1/8 resolution, for every subpixel shift, you predict a flow field, and then you compose this subshifted flow field into the full resolution.
Okay. Another question is, first of all, how easy would it be to adapt this just to rectified stereo, where you have one less dimension to search over? Have you tried that at all?
No, I haven't. I think it should be doable. Basically, when you build the cost volume, you just build a 1D cost volume.
Right.
And you do the 1D search. And the network should be even more lightweighter.
Right.
More lightweight than the flow one.
I mean, the reason I'm asking is because in flow, it seems to the Raft idea seems to be the new state of the art, and
right.
And I would actually be curious to hear your intuition why this is such a big performance gain over the previous methods. But in stereo, it seems to be harder to define what the state of the art is. And so I was really wondering if this could create a similar jump there.
Yeah, I think so from our experiments, it seems this refinement module seemed to be very effective. So, which is kind of similar to learning to optimize.
Yeah.
This module we found to be quite effective. And also another module is to build the full cost volume and also the cost volume pyramid, which in principle is a more accurate search than the warping-based scheme. Because by warping, when the motion magnitude is large, there could be an approximation error.
Okay,
but
great.
When you do the full cost volume lookup, you don't suffer from that approximation. Okay. Any other questions?
Yes. I'm waiting for one last question. Zhengzu Tang, please type in your question.
I don't think he's a panelist, so we would have to promote him first. Or maybe he is?
I thought he would type in the question, but of course, okay.
Oh, here we go. Allowed to talk. Go ahead, Cheng.
Yeah. Okay. Yeah, it's very great work, Cheng. So, yeah, I also observed the same thing for the Middlebury, but because I do everything in a rush, so it's after the deadline. So, so I have the first question is in the Middlebury. I see that in your in the arming sequence, I think that the miniature, the flow of the miniature seems a little bit weird. So do you know what's the reason for that? Is it because the upsampling strategy for the raft, or it's because the initial flow is not that exactly correct? So I mean,
so you mean the result by raft TF this one
yes, yes,
on the
yes.
rifle, right?
Yes, it's the arming sequence of the Middlebury. The two miniatures on the right seems a little bit distorted.
I think let me see. Maybe you mean there are some errors on the two
Leg.
like per two leg? Okay.
Yeah, yes.
Yeah, I think
Looks good to me.
yeah. Yeah, I think something to note is maybe Daniel, you can clarify. So the ground truth or Middlebury has actually be blurred, right?
Oh, okay.
In the visualization, it has to prevent reverse engineering from the ground truth because it's supposed to stay hidden.
Oh, okay.
And then the other thing is the black regions are the half occluded regions that where we don't have ground truth.
Oh,
So,
okay.
but I think it's very close.
Yeah. And another question. Is the time sufficient for another question?
Go ahead.
Yeah, go
Okay.
ahead.
Yeah. Another question is that when I tried the raft code, I found that if I lower the iteration of the raft, it will have some very strange failure case. For example, it will fail on the Sintel ambush 4 sequence for a static scene, but magically it will fix that error after sufficient iterations. So do you think we can do anything about this to make sure that the output will be more stable, especially for the lower iteration case? Because now the main bottleneck for this method is the computation efficiency. So, yeah.
Yeah, I think this may be a research question to how to make it more efficient. And I think if we want to make sure about the performance, it seems from the raft analysis, if also from my empirical study, if you run the iteration long enough, the result basically converge to the same result.
Yes, yeah. So, yeah, anyway. Yeah, maybe we can talk about that offline. Okay, thank you. Thank you.
Yeah, thanks.
Thank you. Thank you for the nice question. And thank you for the nice presentation, of course. I think we go on. We now have 2 talks in concession. It's 2 submissions, one from object detection, one for instant segmentation, both from Xing Yi. So please go ahead and start your presentation.
Okay, thank you for introduction. Can you see the screen, the share screen?
Yes, I can see it. It works.
Okay. Hi everyone, I'm Xing Yi Zhou. I'm going to present our first place solutions for both RVC object detection challenge and instant segmentation challenge. Our key idea is to learn a unified label space from data. So our goal of object detection is to develop a model that can detect all objects in the visual world. We hope a single model can detect animals when we travel to Alaska, detect cars when we are driving, and detect furniture when we are at home. However, this is hard for the current object detectors. Most current detectors are trained on a single dataset with a fixed vocabulary on a single domain. For example, a COCO detector is trained on clean internet images with 80 annotated categories. If we apply this COCO detector to a video we took at Alaska, it cannot detect fish because fish is not one of the 80 categories in COCO. And the detection quality is not so perfect due to there are severe motion blur in our video. So a good news now is that we now have, if we want to detect one specific object categories, it is very likely that this category is already annotated in one existing dataset. As nowadays, we have dozens of good object detecting datasets like OpenImages, Microsoft COCO, and Object 365. So can we train a unified detector on all of them? The short answer is yes. Here's how we start. We can train a unified detector that has separate output heads of each dataset with a shared backbone. It is actually not very hard to make this like code unified detector work if we implement it correctly. Here are some key like implementation details that to make this work. First, we sample data evenly from all the 3 datasets in training, regardless of their original size. And we put one dataset in one GPU so that one network forward only use one head. This makes the training as faster as we have only one dataset. And we only apply loss to the source dataset and ignore the other heads during training. And we use different losses and different sampling strategies within each dataset. For example, we use class-aware sampling for open images and Object-C5 to handle the long-tail classification problem. This model requires a no dataset source at testing to determine which head to look at. As a result, we need the Oracle information during testing. But this Oracle model actually gives a fairly good performance on each individual benchmark. It performs closely with the dataset specific model on open image and Object-C5, and interestingly outperforms the single model COCO baseline with the same backbone. But this is just a single model. However, when we apply this model to an image in the wild, there is a problem because there is no source dataset at test time, and we don't know which head to look at. As a result, we have to put all the output together, and the model may predict multiple nearby boxes, and it is unclear if they correspond to the same instance. What makes it more complicated is that a class may have different names across datasets. Like an open image football is labeled as sportsball in COCO and soccer in Object-C5. So how do we merge these categories? A straightforward solution is to sit down and manual merge. This has been done in MSEC for semantic segmentation. However, this is time-intensive, error-prone, and requires dataset-specific annotator instruction to do well. Luckily, in this challenge, we don't need to do the manual merge ourselves. Oliver already did this for us. And here we select some interesting merges from Oliver's best effort unified label space. So an open image football is merged to American football in Object-C5, while Object-C5 soccer is a separate class. And the Object-C5 wild bird is not merged with other birds. And the animal mouse in open image is accidentally merged with computer mouse in other 2 datasets. Let's look at some example images of football and American football. Probably because Oliver lives in Europe and has not watched an American football game. He didn't realize American football is a brown oral ball that is played by hand. It is more similar to a rugby ball in Europe. But soccer and football are the same thing in any language. Also, it is unclear what a wild bird refers to by just looking at the words. After looking into the category list and images of Object-C5, we figured out that wild birds in Object-C5 are birds that are not a parrot, not a duck, or not a swan. From these examples, we can see that it is quite difficult even for a human expert to merge the categories across datasets. So instead, in this work, we propose to learn a unified label space from data. Specifically, we learn the unified space from the prediction of the separate head detector we have trained. The intuition is that if 2 classes from different heads always have fires at the same location, they are likely to be the same concept. And we can define a pairwise match cost of the unified label space based on the co-occurrence of this detector. Specifically, if we want to merge class I in COCO and class J in open image, we define a cost of this merge is the prediction difference between those 2 classes over all box predictions from the dataset. Note that the network predict a a score vector for all bounding boxes, and we just put all the predicted bounding boxes together and concatenate them to compute the average error. And the cost to merge 3 categories is the average pairwise prediction difference of all the 3 pairs. We can like generalize this to more categories efficiently. With this cost definition, we formulate finding a unified label space as a constraint optimization. The objective is the minimal total cost for all merges here. And we require all classes in the unified label space to be merged, formalized as this linear constraint. And the total number of classes in the unified label space should be within a budget. This is to prevent the optimization algorithm just predicts a trivial merge that concatenates the categories. In our experiments, we set the number of categories the same as the human expert label space for a fair comparison. Also, we relax the integer constraint to a continuous variable so that this optimization can be solved efficiently by a linear programming. And in the end, we use a simple rounding to convert the results back to integers. So if we implement this linear optimization in a brute force way, it requires an exponential runtime due to the need to enumerate all possible merges. And we simply prune the merge space by early removing high cost merges. For example, we early remove merging a car with a table in the label space. After pruning, the overall optimization finished within 1 second for both object detection, which includes 3 datasets and 682 classes, and the instance simulation with 6 datasets and 332 classes. So here is the unified label space we got. It successfully found that football and soccer are the same concept and merged rugby ball and American football. And it also fixed the ambiguous definition of bird and figured out what is an animal mouse and the computer mouse. Interestingly, our algorithm split cocoa oven as an individual category instead of merging it with other ovens. We checked the image in the dataset and figured out why. Because cocoa oven refers to the oven face together with the stove top, while open image oven is only the frontal face. So it is indeed more reasonable to split these 2 categories, even though they are all called oven. With this unified label space on hand, we can chain a unified detector with a single output head. Here is one more detail to make this work. So during training, we only apply supervision to the category in the source dataset. In other words, we ignore the output logits that are not annotated in the current dataset. This prevents false negative gradients due to the incomplete annotations in the unified label space. Also, applying loss this way enables us to apply dataset-specific loss during training easily. Open image requires predicting all labels in a label hierarchy. And for open image images, we use a hierarchy-aware sigmoid cross entropy loss to handle this. And we apply the standard sigmoid cross entropy loss for open image for object-65 categories for object-65 inputs. So let's discuss the good properties of training the network in this loss. It can implicitly handle the class granularity problem between datasets. For example, open image divides person into men, women, boys, and girls, while COCO only annotates person. When training COCO images, the more fine-grained Go output is ignored. So it will, even though we don't know the more fine-grained label of COCO, we can still train the network smoothly. And when training open image images, we apply positive loss to both person and girls according to their label hierarchy. And another interesting thing is, if to train a COCO bucket, but bucket is not annotated in COCO, our loss can healthily ignore the bucket output to prevent adding a negative sample for bucket category. Okay, now let's look at the results. We compare 3 models. The unified model trained with our learned label space, the unified model trained with the human expert label space, and the separate head detector with Oracle head at testing. our unified detector matched the performance of the Oracle model without knowing the image source during testing, and significantly outperformed the human expert model. Interestingly, on COCO, we observed that both unified model outperformed the separate model even with Oracle head. This is probably due to that most COCO categories are merged to one other category in other data sets. So we have more training data for the COCO categories. And let's look at a more detailed per category results. The human expert merge dropped performance significantly on the oven and mouse category due to the incorrect label assignment, while our learned label space can improve performance on all these categories. Also, we actually observe a few categories our learned label space have dropped performance. This is because the total budget of number of categories is fixed in our experiments. And since we split oven, we need to merge other categories. For example, we merge table and desk for two data sets into one, and this is slightly inconsistent. Okay, by far we show how to train a unified detector on the three large and in the world data sets. Here we can also expand our unified label space to include a new data set for domain-specific applications. Here we show how do we add mapillary to our framework for this challenge. So basically, we use an automatic label expanding algorithm that can merge categories if they are already existed in the unified label space, and append the new categories if they are not already in the label space. Specifically, we run our unified model on the mapillary training set. We look at the overlap between our model predicted bounding boxes and the ground truth bounding boxes in the new data set. For each class in the new data set, we count how many boxes of each category in the existing label space have significant overlap with it. If we found two categories always overlap together, we merge these two categories. If not, we just add the category as a new, append this category to the label space as a new category. We fine-tune our model on the new unified label space with our data set after we're doing this. So this is the results before and after fine-tuning the new label space with mapillary data. We find the model gets better on our data sets due to trained longer and have more data. And the model gets the ability to detect mapillary classes comparing to the previous model. Yeah, and this is the model we submitted to the challenge leaderboards. And here we add one more modification. We use a larger test time image resolution for our data sets in testing, because we found this gives a large improvement on mapillary and have similar performance on other data sets. And finally we ranked the first on our leaderboard comparing to other RVC entries. And it's also remarkable that our models are among the top tier performance comparing to other data set specific models. And we use the same method to participate in the instance segmentation challenge in the last 2 weeks. We simply add a mask head to the model and change the data set to the segmentation data sets. So we use a relatively small nest 1-1 backbone and a shorter schedule due to time constraint. In our experiment, we leave Kitty and Wildash for testing only because their training set is small and we want to evaluate the generalization ability of our model. Here are the results. Unfortunately, we are the only RVC entry with complete submissions on instance segmentation check. However, for all the individual data sets that has other participants, we ranked the first and outperformed the baseline. On Wildash, it is remarkable that our results ranked the first place without training on the Wildash training set. Okay, in summary, in this talk, we first point out that training a multi-head detector or multi-data set is not hard if we train it properly by using our data set specific tricks. And we found merging the semantic category across data set is actually hard. And we propose to learn it from data rather than relying on human experts. Yeah, Thank you for your attention. I'm happy to take questions.
Thank you for your talk. Very nice. Let's see some questions. Maybe I can kick this off. So one aspect I didn't quite get is how do you split labels that are in your unified space split and in one of the source data sets are merged? So
Okay. Yeah, this is a good question. So our unified label space will have both person and goal and other fine-grained person together. And during testing, our model will predict the person category and the other fine-grained category. It's so the label space, the learning algorithm learned this merge itself. And right. And doing benchmark evaluation, we will filter out like non-data set category using a post-processing, using the fixed label map.
So in the open image girl case, you also train the person. You also give the person, yeah, okay.
Yes, exactly. The reason to also consider person as positive is we use a hierarchical aware loss.
Yes. And did you add this hierarchy for the other data sets where you had? Okay.
No. Right.
I have a question.
Okay.
So why did you fix the total in your optimization, which is very clever? Why do you fix the total number of categories at the original? Could you allow a few more, say 110% or something, so you don't, if you decide that a category needs to be split, you're not forced to kind of combine two other ones?
Yeah, definitely. We do this mostly for a fair comparison, because so one intuition is we always use use a larger number of label space, then our solution will be more close to the split classifier model. We do it mostly for comparison, but in practice we definitely can find a more optimal number of labels in our solution.
Did you try just increasing that number by 1 and seeing what additional split you get, or what additional label you get?
I haven't.
Thanks. Are there more questions? Please use the Q&A panel function or raise your hand. You can also type in the chat your question.
I actually have an additional question to this work.
Go ahead.
So the question is, so mapillary dataset is much smaller than OED, for example.
Yes.
How did you balance the data between datasets?
Okay, this is a very good question.
Did you balance the data between datasets?
We tried a lot of things, and finally we figure out we keep the ratio to one by one. It works the best given the current evaluation protocol. So for example, if we use less mapillary and more COCO, then we will see a final performance. The COCO performance improved a little bit, and the mapillary performance dropped a little bit. It is a trade-off to the training and testing. And since our evaluation protocol is to treat every benchmark equally, then we found just treat them equally in training is a good way. We tried many others, like more fancy sampler, but don't have a better solution.
Okay, thank you.
Thank you.
Sorry, but then equally means that you just throw them together as is, or you balance so that they all have the same weight at the end. So you counterbalance for the number of images.
We counterbalance the number of images. So we will see more epoch in mapillary than COCO.
You showed on one slide that your performance on the other datasets improved as soon as you added mapillary vistas dataset.
Right.
Partially, you said it might be just because you added more cycles, more epochs, right? Or
right. I think the main reason is we trained. So this red bar is fine-tuned from this gray bar. And we think the main reason is we just trained like half more iterations. So this gray bar is 4x schedule.
Yeah, it would be very interesting to see a third bar there where you have the original model with the same number of epochs as the red model. But yeah.
Right.
And I have the second, maybe just technical question. So object 365 is like not anymore in the final leaderboard, as far as I understand. So you still used it for training, and it helped, or you you sort of used it and then you decided to keep it in the training, and you don't know if it actually helps for other data sets or not.
Yes, we didn't try removing object 365. So we do have tried experiments on just train Coco, and so in the early stage of our project, we just trained Coco and object 365, and found that object 365 actually can help the Coco performance. So maybe it helped.
Okay, thank you.
Okay. Are there any more questions? Please post them to the chat or the Q&A system.
Are we already 5 minutes into the next talk or not?
No. Are we? Okay, we can continue now with the second talk. Sorry, the third talk. Semantic segmentation. Marin, I think you are up. Please start sharing your screen.
Okay, just give me a moment. I hope you all guys see it now.
Yes, it works.
Great. As a matter of fact, we're 8 minutes early, which is great.
Yeah, sorry, I thought there was a second half to Jing Yi's talk. Sorry about that.
Okay.
If you want to wait, are you expecting other people to show up right on time, or are you okay going early?
Well, most of my team is already here, so I'm good.
Okay.
Okay. So my name is Marin Oršić, and I will present our semantic segmentation submission to RVC. Our method codename is shortened from SwiftNet Resent 152 with pyramidal fusion and output test ride 8. I would like to thank Petra Bevandic, Ivan Grubišić, Josip Šarić, and our supervisor, Siniša Šegović, who all worked hard in making this submission. I would also like to thank Ivan Krešo for useful advice, as well as all our industrial partners. There were 2 complete submissions to the SEMSEG benchmark. We ranked first, and the MSEG team ranked second. The result was 4-2, and on the Kitty dataset, there was a draw. There are almost 94,000 labeled images from 7 datasets. There is strong diversity in the content, number of images, number of classes, and input resolution. Furthermore, the total number of classes is over 300, which is over the competition limit. Therefore, we have created a mapping to a universal set containing 193 classes. The algorithm for creating the taxonomy follows 3 simple rules. First, if there are 2 same classes, they get merged. For example, Wildlife Sky and Cityscape Sky are both mapped to Universal Sky. Second, if a class is a subset of some other class, we replace the superset. For example, Vista's van is a subset of Kitty car, so Kitty car gets mapped to both car and van. Furthermore, Viper road gets mapped both to other road and pothole, whereas Vista's pothole is mapped only to pothole. Third, overlaps are split, so there is no overlapping left. For example, truck in Viper denotes trucks and also pickup trucks, but ADE 20K truck denotes trucks and trailers. Therefore, Viper trucks get mapped to trucks and pickup trucks, whereas ADE 20K trucks get mapped to trucks and trailers. Note that the universal taxonomy maps some classes to multiple classes at once, which cannot be handled by standard loss functions. Therefore, we formulate a log sum prob loss, which we call NLL plus, to train multiple classes given a single output. Bolded Pij is a vector of probabilities across all 193 classes at a given pixel ij. Pij is the sum of all probabilities in universal class space to which the correct class C is mapped to, which is contained in the set VC. This negative log likelihood is weighted by two terms. First, alpha ij, which is greater towards the semantic border. And second, the term which penalizes low confidence predictions. The model used is SwiftNet with pyramidal fusion. A single resonant 152 backbone, shown in yellow, operates on 3 scales of the image pyramid. Note that the same color intensity denotes shared parameters across the pyramid levels. The extract features are then upsampled to 1/8 of the original resolution via compact decoders with 256 feature maps. For more information on the model architecture, please see our recent publication. We trained the model on 6 Tesla V100 GPUs. The usage of the GPUs was kindly granted by our partners from vSite. The gradients are accumulated on the primary GPU. However, we do not use BN synchronization. For augmentation, we use horizontal flipping, scale jittering, and square cropping. This table presents some hyperparameters which were modified during training for faster convergence. We gradually increase the random crop size and make the batch size smaller to keep the memory same. We also increase the scale jittering range for each random crop. On epoch 50, we freeze updating of BN statistics, reset Adam moments, and train using 1024 by 1024 crop size. We optimize the parameters using Adam. Learning rate is set using cosine annealing. In total, there were 140,000 training steps, which took roughly 4 days to train. This table presents per dataset mean IOUs for both valid submissions. Our method is designed for large image inference, so we notice weak performance on small ADE 20K image. Poor Cityscapes results occurred due to a mapping bug, which made the model perform poorly on the train class. The bug was resolved roughly in the middle of training, and we resumed using the same parameters. Fortunately, only Kitty and Cityscapes evaluate on the train class. On Wildish 2, we hold state-of-the-art result overall. Also on Wildish, there are negative test cases for which auto-distribution detection is required. Auto-distribution pixels are marked in black. We express auto-distribution predictions as a sum of all probabilities not belonging to any Wildish class. We see that auto-distribution detection performs well in some cases but fails in some other. Here we show auto-distribution detection in other datasets. In Scannet, books on the bookshelf are detected but do not belong to Scannet classes. The same goes for rail tracks in Kitty and cobblestones in Cityscapes. On ADE 20K, less than 1% of pixels are seen as auto-distribution. However, we only submit auto-distribution detections to Wildash. On other datasets, we map from the universal taxonomy to classes present in each dataset. We do this by summing probabilities of universal classes corresponding to the dataset-specific class. In Scannet, we see that the second best class was in fact bookshelf, which is one of Scannet classes. This concludes my presentation. I'll gladly answer any questions. For more info and our model implementation, please follow the link in the QR code. Thank you.
Thank you. Very nice. Thanks. Do we have questions from the audience? already? Okay, if not, then of course my favorite topic would be the wild dash negative test examples. You of course you don't submit them to the other benchmarks. It was interesting to see, however, to see the results on the next slide. On the regular wild dash task, you basically rely on the model to report something from another data set, right? And then you can say, okay, this is so unsure about the regular wild dash classes that it is out of distribution, right?
Yes. So for example, you can see the third picture in the bottom row. So AD20K has the water class or C class or something like that. So this is well segmented here. But on the other hand, you can see that on the top left, you see this funny looking thing. I'm not sure what this is.
It's just a noise image. It
okay.
shows film noise, a film scene where the film flickers.
So we can conclude that the model is confused here. And if I take the class from this would be some AD20K class corresponding to a walkable terrain or something like that. So this is not useful, but it does help in auto distribution detection.
This is just a nitpick. You said in one of the slides that you mapped Mapillary Vista's van class. Do you mean caravan or?
I'm not sure. I don't have the class list, but it can be caravan. Yes.
Yeah, because it one of our topics we have in Wild Dash 2 will be to add this van class to split up some of the confusing labels and make it more clearer. And we felt that van was a missing class, so I was surprised to see it. You mentioned it there. So I think you are referring to caravan.
Yes. So this is very interesting because the previous speaker mentioned that when constructing the unified taxonomy by hand, you are error prone. So yes. This is some of these examples that may happen. Also, I mentioned that we mismapped the train class. So in our taxonomy, we have train and on Rails other, we call it that way. And we didn't map wild dash trains to on Rails other. And that caused the model to train on trains poorly.
Yeah, I mean, you might know that RailsSem 19 is also one of my projects, and we are preparing the next iteration of that. So you can keep. I won't say too much, but there will be a benchmark for specifically for train and train rails and trams and tram rails. So we might have a solution for this specific label. Okay, if we have no other questions, I would say we continue. Yes, we continue with MSEC. Thank you, Marin. And John, please start your presentation.
Can you see my screen all right?
Yes.
Let me see if I can shrink this down. All right, well, I'm pleased to present our work. Our work is entitled MSEG, a composite data set for multi-domain semantic segmentation. And this is work with Zhuang Liu, Oisan Sainer, James Hayes, with Dan Colton at Georgia Tech, Berkeley, and Intel. And first off, I just want to say congratulations to the other winners who have presented today. Fantastic work overall, and really excited to see what you all have done. So each year there are dozens, if not hundreds, of papers published at computer vision conferences about semantic segmentation. And in our opinion, one of the most interesting frontiers is generality and robustness. So just to show you what I mean, imagine a typical day. Say you wake up in the morning, you head out in your car, it snowed overnight, and you head to the office. You're sitting at the office indoors. Perhaps at lunch break, you pilot a drone around briefly, and then so you head back into the office. In the evening, you need to repair your bike. So you head to the bike repair shop, and it's getting late. You head back home, and say you stop by a city plaza at night and check out a fountain, and then head to bed. It's been a tiring day, and if you'll notice that there's a huge diversity of objects and entities and terrain that we encounter, just throughout our normal day, and our visual system is able to function throughout and continue to serve us, and it's amazing. But we don't have anything like that in computer vision today. Nothing that's nearly as general or robust. And the key question that would occur to a computer vision professional is, which data set would I train on? And we know there are domain-specific data sets which are excellent data. They're very fine-grained for driving, also for indoors. And there are also these sort of multi-purpose data sets like COCO and 8020K, which are excellent. But they tend to be a little less fine-grained, and they don't have as much data in specific environments as the previous one. So what we're learning is that no single data set is general enough, and they're all complementary with their own trade-offs. And so the methodology we pursued in our work, we presented at CVPR back in June, was to basically use dataset mixing and zero-shot transfer. So we're going to perform a training test split, not within a data set, which is kind of the prevailing idea, but instead at the level of data sets. So we're going to train on some of the largest data sets, and then we're going to test on data that's never been seen before. And we'd want to have some kind of proxy for, new data in the world that we haven't seen before. And the best thing we have really are these held out data sets that you're never allowed to see during training. And so that's what we call zero-shot cross data set transfer. And the question is, can you generalize to those new domains? And our intuition is that if you train on a mix of data sets, that you're going to gain this this robustness, because these are different data sets collected by different teams, different times, different environments. And the data sets we chose for training were not specifically the RVC data sets, but instead some different ones like COCO, 8020K, Mapillary, Indian Driving Dataset, Berkeley Deep Drive, Cityscapes, and Sun RGBD. And then we're never allowed to see the following data sets during test, but we need to be able to generalize to them: Pascal VOC, Pascal Context, CAMBID, WildDash, Kitty, and ScanNet. And the first operational problem we run into is that every data set has its own notion of what a class is. Xingyi mentioned this as well as Marin. And so we developed some principles, a decision tree, which allows us to decide when can we merge classes, and when do we need to split them, and when can we kind of preserve them as is. And if you refer to our paper, you'll see more details about that. And what we end up is with a ton of merges and splits, and we manually design these by looking at images, and then we use Mechanical Turk workers with about 1.5 years worth of annotation to basically relabel the instances so that they're in accordance with each other across all of these data sets, and bring them basically in accordance with one another. And basically what happens when you do this is, let's look here briefly at some data sets on the right shown here, and then models that will be tested on those data sets. So say we train a model in COCO or just in 8020K, and we want to test it on these data sets, and we're never allowed to see these during training. It's completely zero-shot cross data set transfer. And the question is, which one of these models will transfer best to these test data sets? And specifically, which one will have the highest harmonic mean across those data sets? And what you'll see is some single data set models have really good transfer properties to specific data sets, like Pascal VOC, which is basically a predecessor to COCO. COCO is very related to it, and there's a very good prior there. but it'll fall off pretty dramatically on other data sets, especially, sun will do very well indoors, but it will not do well in a driving data set. But instead, our MSEG model is able to sustain consistently high performance across all of these different test data sets, and the harmonic mean is significantly higher than the best one you could get from a single data set, which is COCO. And we also experimented with comparing with multitask learning algorithms on a subset of these data sets or domain generalization algorithms. And we find that consistently our approach actually can outperform these. And so if we go to our Robust Vision Challenge results, SwiftNet is the winner, and congratulations to them. Our approach is a little different to theirs. So we didn't train on Kitty, we didn't train on ScanNet, we didn't train on Viper, and we didn't train on WildDash. So for these data sets, these are a zero-shot cross data set generalization, and our performance is a little worse on ScanNet and Viper and WildDash accordingly. But we did have superior performance on Cityscapes and 8020K and one of the Kitty categories. So to review the performance, say on Mapillary, our choice of taxonomy was different from theirs. And we excluded a number of categories and basically merged them because some of the principles that I mentioned. And if you consider all the classes, we do lose by about 6%. But if you exclude these classes where we basically get a 0 because we didn't map them, we can gain robustness by 5%, which is an interesting case, when how can we fairly compare different taxonomies? And just a few results here. The Mapillary images are really cool. And we also excluded eco-vehicle from our taxonomy, which, although it might allow us to see underneath the car, it does hurt us in the eco-vehicle class. On Cityscapes, we were able to have pretty good performance there, 80.7%. And you can see the classical Abbey Road photos from Cityscapes. Here's just a few qualitative examples. We had a bit of confusion between bus and train, you can see here, so it's not perfect. On WildDash, once again, we had 0 on a few categories because these weren't included in our universal taxonomy. And once again with SwiftNet, whereas we were about 8% below them, if you consider all the classes, if we exclude categories where they get a 0 and we get a 0, we're about 3% behind them. But once again, ours was zero-shot cross dataset generalization, whereas they trained on it. And here are a few fun images from WildDash. Kudos to Oliver and his team for collecting a data set. And one of the negative examples, which we're still able to basically reason about. On Viper as well, here are a few results in the kind of the synthetic Grand Theft Auto world. The boundaries of the billboard are a bit difficult for us. And here's 8020K. It's a little low resolution images, a few qualitative results. And then on ScanNet, we're not perfect as well. We saw a counter here where we shouldn't have, and we thought that this counter was table. Yeah, so that's pretty much our presentation. Thanks for listening. And our code and models are available online in GitHub. I welcome you to check those out. Thanks for your time.
Thank you for the presentation, and thanks again for your help with the RVC dev kit. It was a real, it was really helpful to have you supporting me with that, especially, of course, for the semantic segmentation part. Yeah, do we have some questions in the audience? Please come forward. I will kick it off. You showed a slide where you compared the performance of the MSEG with MSEG without the relabelings, the mechanical Turk relabelings, right?
Right. Let me find that.
And what I found really interesting is that it's even without the mechanical Turk relabelings, you are in many categories in many rows, you're still quite near to the best or the best entry, right?
Right. We had in our paper, we have a little more detailed comparison about if you have a naive merge of the categories, where you basically just merge them if they have the exact same name, ignoring uppercase, lowercase, and you'd end up with about 316 categories, and we trimmed that down to 194 through a lot of tedious effort, kind of manually examining these classes.
But what I mean is the relabeling, where you add more supervision basically to the data sets. If you have not this amount of resources, if you just have the plain data sets, how much does the performance of MSEG drop without the additional labels, the splitting?
So it dropped here by about 2%. We saw something similar on the training data sets as well. If you test on the val split of the training data sets, but forming that unified taxonomy is really important. We find that was really important.
So the Mechanical Turk additional labels are not actually adding that much. I mean, of course, they add the last fine detail bits, but all in all, you can get quite far without it, right?
That's true. We did see a lot of kind of frustrating errors where every data set has a notion of floor, say carpet or table and counter and cabinet, and qualitatively it was poor without, in many indoor scenes, without that that extra boost.
Was there like a specific data set that you think improved much more by having these additional labelings? So is there basically a very fine-grained data set, or one that's too coarse for your liking if you need to mix the domains?
We saw a performance improvement of about 4% on ScanNet with the relabeling. So I think indoor is where it really makes the biggest difference.
So there was the most confusion was between the ScanNet and the, I guess, Coco or VOC labels, right?
Right.
Okay, do we have more questions?
I have a short question.
Go ahead.
So thank you for the presentation. The question is regarding the per class IOU on the Wildlish dataset. How were you able to see those?
Let's see, I clicked around to the, I guess, extended metrics table, and then...
Yeah, I can answer that. I programmed it. There is an extended view, yes. If you look at the regular board, you see a button that says extended view, and then it opens a full table where you have a drop-down menu where you can look at each of the metrics and each of the class labels, and you get the full table. So the front table is basically like a recap of these extended views. The extended views is for nerds, for statistical nerds, and for people that want to look at specific details. But it's not for the average visitor, so that's why you need to click on this extended button, because in the beginning it was the default view and it was very confusing to a lot of people. So I added this overview, basically view, and then you have to click on the extended view.
Yeah, thanks. I'm asking on behalf of some guys who would like to see all the metrics.
Yes, you have the same functionality at Wildlish 1 and 2, so you can look at the historical data as well and see all these fine-grained metrics.
Okay, thank you, and once again, thanks, John, for the work.
Oh, thanks, everyone. Congratulations.
If there are no other questions, I'm still interested in one thing. So maybe for the future, I don't know if you have something in your pockets, in your sleeves, and if you want to talk about it openly. One problem is the classes you can't relabel, that you have to split. So if one of the examples we saw in the other slides was this oven versus oven and countertop thing. So in one data set, it's an oven, and the other data set it's an oven and a countertop. They solved this by using these negative labels and basically having 3 labels, like a combined oven and only the oven front and only the countertop. And then depending on the data set, you choose which of the logics you actually look at. But to stick with more your kind of approach, do you think there is also a more or less unsupervised way to split such labels?
In an unsupervised way, it seemed like Xingyi has a pretty good approach. You mean without any manual supervision? I guess you can merge those in kind of an oven stovetop class. That's effectively what we did.
Yeah, but I mean, even better would be to have like a, or I don't know if it's better, but I assume if you have some unsupervised approach that generates this borderline then and splits this, for example, oven into the countertop and the front part. So something like we've seen in the keynote by Kwok Lee, where you basically have a teacher and a student kind of setup. So could you iteratively learn unsupervised to improve the borders and to split these labels that you previously identified?
I'm sure there's a way to do it. I think Marin and Xingyi presented some interesting approaches that are worth pursuing further.
Yeah, it was just something that popped into my mind as I saw your presentation. I think it could actually work and produce a much fine-grained data set with the same data you already have. So I'm a bit skeptical about using a lot of mechanical Turkers to do anything. It is necessary for reference data sets and for groundwork, but at some point we have to get away, is my opinion, we have to get away from all this supervision. We have to get away from manually annotating a lot of things, and it's not the same thing as only relying on few-shot learning. I think we have to get much more toolkits in our repository of how we deal with these tasks for unsupervised and semi-supervised learning, and I think it's going into this direction.
I agree.
Okay, if we have no other questions, let me have a look at the chat. No. Okay. I don't see one of our keynote speakers here. Do we want to make a short panel question round? So maybe to close the workshop, one of the questions I would give to our organizers is, what did you find, what did you summarize after looking at all the participants and their presentations? What did you find the most interesting or most surprising aspect, and so challenge-wise, how we asked them to combine so many data sets, and what is your take on the RVC? Did we in any way create a more robust solution now that we tried to more robustly evaluate? What's our legacy from this year?
I think what's interesting is like all this taxonomy work. I wonder if it would be interesting to have a challenge or benchmark just on taxonomy, merging, splitting, and operations.
Yeah, I think in a way, what we are doing is something like that, right? So if you are good at splitting and merging, and the thing I was just musing about of unsupervisedly and basically improving the labels that you are missing, then I think you're bound to be better in the RVC in these kinds of challenges, right?
Yeah, sure, but you have to solve lots of other tasks.
How do you suppose we could evaluate just the splitting?
I mean, maybe just actually make a data set from multiple like benchmarks and make this a challenge, like of course the fixed like target and so on.
You can also unify the models, right? Like right now you need to figure out the assignments, the data, and also the model itself needs to be trained, right? If we unify the model, like everyone needs to use the same model, so they can only play with how they handle the data. that will be a way to kind of focus the effort there.
Okay, yeah.
That's a cool way, actually. I
Yeah,
think.
yeah.
I like that idea. I think also if we can find a way to maybe make it more like zero-shot cross dataset generalization, where you're really testing on data you haven't seen before, I think that could help as well to kind of level the field.
Do you think it would help? So this is an open question. Do you think it would help if we have a more shared and more common baseline for all the labels, like a more common hierarchy and taxonomy? We have WordNet, we have the Freebase IDs, some Wikidata QIDs. So just as a bit of background, the label policy or the unified label space I created with the help of my colleagues is basically based on automatically matching the labels so the names of classes to these kind of IDs to get as many actual hard numbers that try to grasp all the nuances. But we have all these different things, and unfortunately WordNet and also Freebase are basically dead. So do we need our own standard? I don't know. Is that a thing we need? Should we rely on what's currently there on hierarchies and taxonomies, or do we need an own computer vision taxonomy?
Well, let me ask a question. I'm not an expert at all on these labeling tasks, but I thought Ross's keynote was very interesting, and he addresses that in a different way using his Elvis challenge, right? And so I was actually thinking, is there some competition going on between these different efforts, or is it basically unrelated?
So Elvis is more about the long tail of the distribution. Their approach to define what's interesting or what should be a category is basically the other way around, which is very interesting. Normally you have this task-driven approach. You say, okay, in our task we need to find the cars, so car is a category and so on. And then in Elvis they started with the images and said, okay, try to label all of the images, whatever category.
You don't have the problem of having to merge incompatible label sets or hierarchical label sets, right? So that's somewhat a different issue.
Yes, yeah. And the other issue, is which kind of language do we fall back to? A lot of the problems I saw in RVC was that categories have different names that are the same and the other way around. They have the same name and mean different things. A perfect example was this Affen case, or I saw one example was balloon. So balloon is sometimes the hot air balloon, sometimes the party balloon. And I think in one of the data sets it was both. So you had the same label for both, and in one you had one label for the one thing. And so if, of course we have taxonomies, of course there's all this natural language learning and turning language into numbers. We have taxonomies, we have the whole WordNet and all the other things, but do we need something of our own, or do we need?
It's not going to solve. It's not going to solve it. Like at least I think I've been around this question now for a couple of years, and yeah, it will help. And we do we have used similar tools in the past. But then you enter into different type of problems. Right? Like the typical example I like to think is like, even if you had unified all the persons in different data sets to the one entity person that is like a codified with a number, then you still have the issue that there's different definition of what a person is at the pixel level, right? Which then reflects the bounding box level, which reflects to pretty much most of the tasks. A typical example of this is the helmet part of the person, yes or no? Is the backpack part of the person, yes or no? So you might still be kind of grosso modo referring to the same thing, but then when you get to the specific extent, that does diverge and does become either ambiguous or application dependent, depending on the cases.
Maybe I'm thinking of this in another way. So what I'm suggesting is that we have a very, very concrete definition of those classes then. So if we say person, then we mean the following thing. And from
that doesn't work. this I can guarantee doesn't work, because I spent almost a full year doing it. So
Yeah.
that's the reason why OpenImage v5 has only 350 categories for semantic for pixel level labeling. And the reason for that is because the bottleneck of the process with the resources we had was defining the categories. So we had enough annotators, we could annotate the full data set for a new category in 2 days, but defining what exactly means to be a potato is like a week-long effort. Like if you peel a potato, then the potato peel, when it's connected, that's still part of the potato, yes or no? And when you cut it, is it part of a potato, yes or no? And if you dice it, is that still, you can tell it's a potato dice, is that still potato or not? Is a potato puree still a potato, yes or no? The simplest concept, like if you have a potato, you leave it 1 week and you see the leaves growing. Are the leaves part of the potato, yes or no? So even the simplest concept like a potato becomes very hard right away.
Yes, but why don't we collect the answers to that? Why don't we collect numbers basically that define, okay, if I refer to a category 1105, it's a potato with the peel, yes, the plant, yes to the dish. If I refer to number 7175, it's only the peeled potato and so on.
Well, but we can keep track of that. I think it's a question of scalability. I agree with Rodrigo. Can I interrupt you quick, because we have 9 panelists and we have 10 attendees, and I'm just gonna make all the attendees panelists in case they want to ask questions too. There's no real reason to stay separated. Is that okay?
Yeah, sure. Go ahead.
I'll just add them all to the room.
Yeah, it's exactly a scalability issue for sure. With that, you can get to hundreds, but not to tens of thousands.
I think I mean, this is exactly the reason what makes this interesting to like just regard as a problem in itself, right? I mean, to not say, okay, we should have this new, maybe new taxonomy, but just say, okay, taxonomy is a challenge by itself. Let's make it a benchmark, and let's see what solutions people find. And they could use Turkers, they could use 1 million classes, they could use self-supervision, whatever.
I guess one of the issues you also encounter when you approach it this way is that you realize basically as you move forward into what does the visual world means, you realize that humans are very inconsistent. They're inconsistent with themselves, they're inconsistent across themselves, and they're also inconsistent across different cultures. And that happens pretty quickly. Let me, like an example of this was, so olives, people don't agree if it's a fruit or if it's a vegetable, or if it's a nut. And at least psychological studies have shown that even that is not consistent through time. So you can ask a person 1 week and then 2 weeks later you ask again and they will answer something different. So if you do anything like that, it has to be accepting the fact that it will be noisy and kind of probability distribution and there won't be a right answer. Other examples we had was like, people don't know what baseballs are and cricket balls are, depending on which side of the world you are. So some people tend to think that a lot of cricket balls are baseballs, and a lot of people think that baseballs are cricket balls because they have different priors and biases. So it will be very noisy very quickly. And so if you keep that in mind, then maybe you can dare it, but otherwise when it gets noisy, you lose some of the benefit of having it attached to a number.
So just to interrupt, it seems like the discussion is getting very specific here, and maybe we should also kind of go up a little bit at the higher level and talk about the whole RVC and what worked well and what didn't. So, I mean, I'm happy to keep talking about labeling issues, but I think there's also some bigger questions we should discuss.
I agree.
Any thoughts? Anyone has any thoughts?
I guess I'm curious with the questions. Like, now that we have done this experiment, at least for me, it's the first year I'm part of the team. What are the specific points we can pinpoint that we got the benefit of having multiple data sets instead of just having had one bigger data set? Just like, if you basically take the biggest data set of any of these challenges, do we really get different conclusions when we have this diversity of data sets?
So I certainly think that's the case. And I mean, again, I mostly know about stereo, but the trend that I see is the large data sets that come with a dedicated training set. A lot of papers, people just train on kitty and test on kitty, and then that's the only experiment you read about. And so anything that forces people to test on more diverse data is important. And of course, if there was a super duper data set or benchmark that was as diverse and as big as it could be, then that would be good. I mean, just looking at the last few talks, I thought it was super inspiring to see these efforts on zero-shot transfer. And I mean, that is a goal, right? You train on something and you test on a totally different data set and you still hope it does well. And so I think in that sense, what we're doing has value. The problem that I see is that it becomes very hard to participate. And we had many fewer participants this year than we had 2 years ago. And partly that's maybe due because we had more benchmarks and more data to work on, and a huge effort to write the development kits and all that sort of stuff. But if you think about what will make this successful, it will only make it successful if it becomes some sort of standard. And if the reviewers start to say, hey, that's not enough if you just send us this one benchmark result, show us the results on RVC. You know, that would be the ideal scenario, but it's probably not going to happen. But so I think it's a fine line. We have to make it easy enough to participate, but hopefully the challenges are going to give better insights on robustness than any single benchmark.
I think there are some possibilities we can lower the make it easier to participate. Like currently, it's like you have to download, and the download is not that unified depending on like the toolkits. I only know depth prediction, and especially submission is, of course, we have to submit to every benchmark individually. And if you like in the long term think about, okay, could we maybe at least for some tasks unify the submission and the download completely, so you have like one kit for downloading and one kit for submission. I think this could like make this much more easier.
Yes. So I just want to say I definitely second sort of Daniel's first point with the diversity. I mean, I think especially kind of in the low level or more low level benchmarks, right? Like depth estimation and flow. It's like so much is dominated by these sort of autonomous driving data sets that basically if you do depth prediction and you kind of just predict this corridor of a street with houses, like you're like 80% there to a good solution. And that doesn't make sense. So I think it's in those data sets, it's really like important to have these, have something like Sintel and maybe ScanNet and so on, like it just a little bit more diversity. And I wonder in the future if it would be possible to actually have similar zero-shot approaches for those tasks too. Like if we say we have like a stereo or a flow test set that at the point of the workshop, there's actually no training data available. And then people can test on that. And then after the workshop, maybe if it's kind of going to be a larger benchmark, it can be available, but sort of if that would make sense.
Look at Kaggle challenges, and then if you look at VOC, object detection, much older challenges, that's the ultimate way to test robustness, is to have a one-shot contest, right? As soon as the data is out there, and you need to come up with mechanisms to prevent overfitting. That's an age-old problem. But it takes so much time to gather a brand new data set that no one has seen before, right? So that's a separate issue. And then you still need to, so one thing that I see with benchmarks is they also need to take off. If you have the super benchmark and only 3 people participate, no one knows about it, no reviewers will ask for it. And so we've seen plenty of good benchmarks that haven't really caught on. And that might actually be another side effect of RVC, as there's some sort of publicity associated with it, and people participate and then all of a sudden say, oh yeah, now I can participate to this benchmark that I didn't know before, and it's a good benchmark. But so there needs to be momentum, but then the conflicting thing is that the longer it exists, the more overfitting happens, and so it's kind of find a balance between the two.
Let me try just to challenge ideas to see to see a different perspective on this. So the way I see it from how I saw this it went this year, there's basically two different set of challenges. There's the set of challenges that have this kind of low level component like stereo optical flow and depth that don't have a semantic ingredient and have kind of their own difficulties, usually in the type of scenes that will appear and type of resolution that will appear if they're RGB or color. But that's the kind of type of variance and problem. And then there are the ones that do have a semantic ingredient. And then we have all these kind of how do you merge, which are the concepts and so on that we mentioned. And then the notion of zero shot in these two are a bit different in the sense that zero shot in the non-semantic case is more like complete different type of images or the complete different type of scenes or different areas of the world. While the semantic one usually means like the new categories, just like these new categories you haven't seen before. So a question that I have trying to compare different alternatives would be, how would it look if we did a different type of robust vision challenge where we don't have multiple datasets, but we explicitly say every single year we take a new mix of datasets where for the non-semantic task, we're just going to put in one bag a somewhat random subsample of images from different datasets. That's your training set. And then the held out test set is going to be a different sample, right? Maybe even from including some different datasets, right? Some overlap, some are different. But then it's only one data set, and it's only, so it's like one thing to download, one thing to upload, and we define the one benchmark, so we don't have these multiple benchmarks put together. That will still have all the diversity. That will make it easier to participate. We could even keep it fresh because every year we can resample differently. So it's like the same type of problem, but not exactly the same images. And for the semantic part of the problem, we can do the same thing. And the zero shot aspect is that, well, you will know in advance that the test set will include classes that are not included in training set. So that right naturally will do this, will have this effect. So that would be another way to combine multiple data sets in a way that is easier to participate. And I wonder, that's a question for the discussion, is like, doesn't that capture pretty much everything that we still want to have?
I think it does, but I see two problems. First of all, it would be a lot of work to pull this together. And second, you might still not get very many people who participate.
But that is the same as this year, right?
I mean, it was already a lot of work in this round to do the dev kits. I think Oliver did most of this work. But the idea with this, the current type of challenge is we kind of piggybacking off the work that other people have already done, namely getting a benchmark running, which is so much work. So to define anything new, I mean, it would solve some other issues that we had, like incompatible metrics and all that sort of stuff. But even if we did it, and even if we found people who had the energy to kind of mount these challenges, how would we then get a large number of people to participate? I don't know.
Well, and there's another issue there, is at least for kind of the low-level challenges, right? The test sets are already fairly small. So if we like subsample them even more, then it might just get either more noisy, or we actually don't have the, like, if, I don't know, if we have something like Scintilla and we kind of subsample different frames from the same scene, like the variation is not that high. But if you sample whole different scenes, then like you actually don't have that many scenes to sample from. So it just could get very noisy.
Okay, it was a bouncing idea. I think anyways, the challenge as we have, it does take a lot of effort. And as you said, it's like basically trade-off between different set of problems. Yeah, but at least for this aspect of ease of participation, that in my mind becomes the easier to participate and easier to identify. But I see that there are trade-offs.
Yeah, one aspect I wanted to mention is maybe one of the things that also Daniel said. One aspect of RVC is that we promote basically new data sets, or that we give new data sets a chance to be visible to people that only have a very narrow way of evaluating, that only use always the same data set. And my hope actually is that we also influence reviewers. So if this whole thing gets more visibility and gets more people to participate, then also the benchmarks that are in RVC will be requested in the next year or the next years by reviewers. They're saying, why did you only evaluate on the old data sets? There are these 3 new bright data sets that we want to see results too. So it should piggyback in a way, because we want to promote creating data sets. We want to promote maintaining constant data sets so that people can have a reference, can see progress. But of course, at some point, I think everyone is aware of that. At some point, a benchmark has had its life and basically is overfit, and we don't see that much new on it anymore. So that is not a problem. I think it's very acceptable, as long as we are aware of it and we have progress also in the benchmarks. And currently, I don't think that's a problem. So I really think it boils down to usability. If we make the challenge more accessible, if we make the dev kit and the way the progress, the process of registering and downloading and submitting, just as Hendrik said, if we find a way to make this even more appealing and more easy to use, then it will work better, I think. And yes, we have to remove some of the data sets that we think are outdated or that don't add any kind of new information, basically. If one data set is a complete subset of others, yeah, I don't want to say we drop it, but we have to select some.
I've toyed with the idea of turning off Middlebury Flow for a long, long time. And I found it really interesting to see that in this challenge, people were not training on it, but still testing on it and then doing well. I thought, wow, well, it still has value.
Yeah.
What was I going to say? Oh, yeah. So one big issue we had in this iteration was depth prediction, because all of a sudden we have methods like metas, which are actually designed to be robust. It seems like the poster child of a method that should do well on a whole bunch of different things, and then its performance was not properly measured by Kitty. And so that is another issue, because if you have old established benchmarks, do we have to throw them away? Do we have to throw them out, or can we tweak them? You can't just change the metrics, because then the whole table of results. I mean, I had 3 generations of the stereo, and every time you see the new table, at least you already have the visibility, so people know about it, and it's not as hard as starting from as a totally new benchmark. But
do you keep all? Sorry. Do you keep all submissions, all old submissions? Could you rerun with new metrics?
Back to the old table when we shut it off. But you need to resubmit. I mean, typically it's new data sets, new metrics, everything. So you just have to start over.
No, I would challenge that. If you keep all the submissions, then you could, for example, now for the monodev case, now you could add a new affine invariant evaluation metric, and then rerun all and get a new.
We could have this discussion with Jonas, I guess.
Yeah, I mean, especially if we just for the future with sort of the Sintel depth thing, I think it would be important to yeah, maybe rethink the metrics we kind of stole from Sintel and see. I mean, there are a whole bunch of new metrics, right? Like you could also do the whole masking thing. Like, okay, now we can actually get evaluates of depth estimates near ground truth depth boundaries. You know, and all these things that we do sort of with flow, with these different masks and occlusions and so on. Like we could do similar things for depth, and I think it would make sense, you know, given the time.
Yeah, I think it's already getting late, and I feel like we have reached a good conclusion and a good point to stop. I have one last slide here for the video, so that the video ends with it. So I will put it up. Yeah, to anyone, please visit the website, robustvision.net. We will have all the videos up there. And with that, I'd like to thank all of you again. It was a very challenging time for me to put up the challenge. and your help was very, very welcome. And you also had put a lot of hours in many days. So thanks again, and yeah, good night.
Yeah, well, thank you. You did the most work, so.
Yeah, thank you very much.
Thanks, Oliver. Thanks.
Thanks. Goodbye.
All right. Bye, everyone.
Bye-bye.
Bye.
Bye-bye.